Hello guys, can you hear me? Please confirm. Um, okay, let us wait for 5 more minutes for some other people to join and then we'll start.
Everybody, my name is I'll show you a really simple way how
Okay, so we will not wait anymore and we will start. So you can see my screen. Can you guys hear me? Please confirm that. Just write yes, no, anywhere, anything. Can anybody please confirm if you can hear me? Okay, thank you, Sushmita. So today you can see that we'll be talking about some problems which are related to what you learned in your last class on atomic and molecular physics. Okay, so the first question being, and if you have any problem anywhere, please stop me and ask me. So the first one being that what is the electric field that is needed to pull an electron out of an atom in a time comparable to that for the electron to go around the nucleus? What is the meaning of this question? So what do you think? And over here, let us consider a hydrogen atom, okay? So let me write. This is an addition to the question. So what do you think? Any guesses? See, hydrogen-like atom, what will be its charge? Okay. So this is Ze, right? This is the nucleus, and you have an electron here, only one electron. So what is the nuclear charge? That is equal to Ze, right? So the ionization energy, what is the ionization energy of a hydrogen atom? What will this be? Now it is 13.6 so Z square, right? EV double. Okay. So the hydrogen atom needs, in a hydrogen atom, if you want this electron to go out, you need to give minimum of this much energy, isn't it? Or if you want this to get excited to the next level to a higher energy level, you need to give this much energy, right? So now if this is the energy that you need to give, but in which form are you giving the energy? Say it's an electric field, okay? So let us equate this to an electric field. So, so the force due to an electric field, you know that it is always for, wait 1 second, this is always this, right? Where E is the, where you know E is the electronic charge. So this is the force. So what is the energy? Now how much, now if you have a force and you want the work done or the energy, you always need a distance, right? uh, Along which the force is acting, okay? So multiplied by the distance, F into D. So what will be the distance here? Here it will be the Bohr radius of the hydrogen atom. Now what is the Bohr radius? Can anybody tell me that? What is the Bohr radius of the hydrogen atom? Let me write here, in multiplied by the Bohr radius. What is this? This is the definition of a Bohr radius is, this is the probable distance between the nucleus and an electron in the ground state, okay, for a hydrogen, okay? So let me write that here. So this is the most probable distance between the nucleus and electron in the ground state. Okay, so this distance is, say, the Bohr radius A. Okay, let this be A in this problem. So let us put this. Okay, for a hydrogen atom, what is the Bohr radius? For a hydrogen atom, this Bohr radius is equal to 0.53 into 10 raised to the power minus 8 centimeters. Okay, so this will be E A. Okay, so okay, somebody wants to join. 1 second. Okay, oh, sorry, she will join. Okay, so so now you can understand what this problem will be. So this force that we are giving, this force should be greater than equal to this energy. Therefore, this E, and A, that should be greater than equal to 13.6. Z is 1 here. That's it. So find the electric field. 13.6 eV divided by whatever is the value of E and A. If you put the values, what do you get? Can anybody do that? Do this calculation? Okay, this should be around 2. I have the answer here. 2 into 10 raised to the power 9 volt per centimeter. Okay, so you need this much of electric field to pull this electron out of an atom. Okay, I have assumed hydrogen like atom. If it's just any other atom, you have to put, instead of Z, you put that uh, value of whatever the atomic number is of the other atom. Okay, so this should be greater than equal. Now you have taken the Bohr radius. So for any other atom, it should always be greater than the Bohr radius of the hydrogen atom, right? So this force should always be greater than equal to this much, this electric field. Is this clear? Does anybody have a doubt in this problem? See, it's a very simple problem, but the way this question has been stated, it seems that where should we get the electric field from and all. But if you think about it, it's just, you just put in a few, information that you have. Okay, let's go to the next problem. Please read this carefully. The ionization energy of the first three elements are, you have hydrogen, helium, and lithium. So can you tell that why this ionization energy EI, why is this different in this fashion for these three atoms, for these the elements that are mentioned? Can anybody guess that? Any guesses? Why does the ionization energy EI change like this? Why is this the lowest for lithium and highest for helium? So can anybody tell me that why does the ionization energy of the elements which are given here, why do they change like that? Why is it the lowest for lithium and the highest for helium? This is a very, conceptual question. And if you can answer this, then you really have good concept. Okay, so let me explain. That is, you see, hydrogen and helium, right? What does what is the atomic structure? Something like this. This is hydrogen, and you have one electron in its outermost shell, and inside you have one proton. The proton, I am marking it with a hollow circle. And does it have a neutron? Anybody tell me that? Is there a neutron in the hydrogen atomic structure? Yes. Hmm. Anyway, so okay, one proton, one electron. And for helium, what does this what happens here? Something like this, right? You even have a proton here now, isn't it? So you have plus 2e here, and here you have minus 2e outside. So you can see that for hydrogen, so now can you tell me? Now can you guess why is the ionization energy of helium more compared to hydrogen? Okay. So you see the nuclear charge. All of these, each electron here will face the same force from the proton, right? From its nucleus. While a hydrogen atom, the electron in its shell will face lower nuclear charge. So this has a lower nuclear charge. Okay, so if you want to eject this electron from the outermost shell of helium, you need to give a larger amount of energy because plus 2e is attracting, and for hydrogen atom plus 1e is attracting. Is that all right? So the ionization energy of helium is more compared to hydrogen. Now what about lithium? Why is it so less? It's even lesser than hydrogen. But I think it has more nuclear charge, lithium, and more number of electrons. So why is this so less? This is so less because so what do you have for lithium? How does that look like? So here you have plus 3e and first shell is complete. You have another shell here, one more electron, right? So here the inner electrons, let me draw it here, 1 second. These two inner electrons, they are shielding the charge. They are shielding this plus 3 nuclear charge from here. Okay, so the outermost electron, which is this one, this cannot see the full nuclear charge. So this charge which the outermost electron is seeing, that is screened by the inner electrons. Let me write that down here. So the valence electron, valence means the one in the outermost shell. The valence electron feels screened nuclear charge. Okay, therefore this has a low ionization energy compared to hydrogen. Is this clear? Okay, now the second one. What is the second ionization energy of helium? What do you mean by second ionization energy? What is the first ionization energy? What is the second? What is the third? Can anybody tell me that? Okay. So suppose you have some atom with some nuclear charge Ze and it has its shells, electrons. Now let us just consider the valence electron. Say it has 4 electrons in its valence shell, the outermost shell. So the energy which is required to take out 1 electron from the valence shell is called the first ionization energy. Okay, and so when you take that out, you already have a vacancy here, right? I'm just deleting this. So it looks something like this. Okay, let me just delete that. Okay. Now, now the energy which is required to take out the second electron, that is called the second ionization energy. Is that all right? So, uh, so what will be the second ionization energy of helium? So let us draw helium in such a state where its first electron is already not there anymore. Okay, so you have plus 2e at the center, and in its valence shell you have one electron, not two. So right now it is hydrogen like. With one electron removed, isn't it? You will agree with me, right? So now we can apply our normal formula, whatever we have. So you know that the energy levels of a hydrogen like atom are given by, what is it, minus z square by n square. Okay, sorry, we have a minus 13.6 here, n square, right? For hydrogen you don't have the z term because you know z is equal to 1, but I am having some other atom here, so I will put the value of z. Okay, so here z is equal to 2, so you multiply and see what is the value. N is of course 1, and you'll get something like 54.4 eV. Is it all right? So this is the second ionization energy of helium. What is this? The second ionization energy of helium. Is that clear? Does anybody have a doubt in whatever we have discussed so far? Yes, Amit, you want to say something?
No, I don't have any doubt.
Is this clear, this problem?
Yes, ma'am.
Okay. Okay, then let's go to the third problem. So you have a beam of electrons used to bombard gaseous hydrogen. So what is the minimum energy in electron volt the electron must have if the first number of the Balmer series corresponding to transition from n is equal to 3 state to n is equal to 2 state is emitted? Basically, they're asking for the energy of the first, the Balmer series of hydrogen spectrum, the first line, basically. So what is it? Can anybody calculate and let me know? Give us some time. You all must be knowing how the lines of the hydrogen atom, the hydrogen spectrum, look like. I'll just give you a short revision. That is, say you have the energy levels like this. You know that it keeps on decreasing as we go up. Okay, so this is n is equal to 1. The first energy level, n is equal to 2, 3, 4, 5, 6, and so on. Okay, so all the lines, all the energies which are given out when an electron falls from any of the states above to n is equal to 1, any of the states above, any line which falls back to the ground state is what? This is the Lyman series, right? And any line or any transition which takes place with the electrons falling to the second, sorry, I did something wrong, to this n is equal to 2, that is the Balmer series. Similarly, all the lines, I should have drawn some more lines. Similarly, all the lines which fall to n is equal to 3, what is it called?
Gaussian.
Yes. So the line number or the energy level at which the electrons are coming back, that is only important. Okay. So first line means what? Just just the electron which is taking, transited from the energy level just above it. Second line, the one on top of that. Third line, the one even on top of that. That's it. So we are interested here in the Balmer series. So the first line, that means n is equal to 3 to n is equal to 2. That is pretty obvious as mentioned in the question. So what is the minimum energy that the electron must have? So if an electron makes a transition from n is equal to 3 to n is equal to 2, what is the energy that will be emitted? How will you do this? It is already given that you have hydrogen here, so you need not worry about any Z and all. It's just 13.6. So the energy required, or the energy that will be given out, that will be 13.6, and in 3 square minus this, right? Sorry, n2 minus n1. So for us, the second line is 3. So 3 square, and the first line is 2. So what is the answer? Let me know. this will be something around 1.88 electron volt. Okay, pretty simple. Okay, now let us look at the next question. It is similar. So a hydrogen atom, initially at the ground level, it absorbs a photon and gets excited to the fourth level. So calculate the frequency and wavelength of the photon absorbed. So in the previous question we were talking about emission. Here there's a transition from the 3 to the second one, right? So it's going down, so there will be emission. But here it's something reverse. Here the electron is going up from the ground to the fourth level. So what is the wavelength of the photon which is absorbed? Are you guys doing this? Are you guys trying to solve? Okay, so you know the energy is for a hydrogen atom is given by minus 13.6, and you have 1 by n1 square by 1 by n2 square, right? So here E1 is equal to minus is the ground state, because the atom is taking N1. What is N1? The first level of transition, and N2 is just the second level, just the difference between two levels. So for us, N1 is 1 ground state, and the second level that is being talked about is the fourth state. So N2 is 2. So now okay, so just this is E1 by 1 square, whatever. The second level is minus 13.6 by 4 square. Okay, so what is the energy that was required for this transition? 1 by 1 square by 4 square. What is it? Let me know. What does this come out to? 12.75. Have I done some mistake here? I wanted a plus sign, but I ended up with a negative sign. Can you help me spot the mistake?
My answer is 12.5 electron volt.
12.5.
Yes, ma'am.
Have you not like followed along? I mean, you got this one right? Just
Yes, yes,
hmm. And you're using 13.6.
yes.
Okay, I'm getting a 12.75 using my calculator.
I will
Okay,
recalculate.
it's close. Yeah, it's close. Okay, so of course, then the frequency and wavelength of the photon absorbed. So you know E is equal to h nu. So from here, you just put 12.75. I'm just taking the absolute value. I think I have messed up with some negative sign somewhere. So you put in the values and you find nu. What is it? Let me know. So 12.75, it was electron volts. So I will multiply it with the electronic charge by H constant. The 6.6 into 10 raised to the power minus 34. So this will come to around 3.07 into 10 raised to the power. The order must be correct. Like instead of 3, you cannot have a 2 or something. So this is the frequency. And the wavelength, you know that the velocity is given by, okay, let me not write C. C stands for light velocity. Just a constant reserved by the physics community for the velocity of light. So let me just write a normal V is equal to lambda into the frequency. So from here we get the wavelength. Okay, using a photon here. Okay, yeah, we'll use the velocity of light itself. Lambda is equal to C by this. What is this? We are supposed to get something like 97 nanometer. Okay, this is the answer which I have here. Okay.
Ma'am, can we apply that formula which is 1 by lambda equals to R 1 by n square minus 1 by n2
Wait.
square?
Yes, yes. What? Repeat. 1 by
There is a
lambda.
formula 1
Hmm.
by lambda equals to R
Hmm. Hmm.
1 by n1 square minus 1 by n2 square
Hmm.
for the calculation of lambda, and then we will proceed by
Yeah.
for the
Sure. Then what should you put in the value of R?
R is Rydberg constant.
Yes, you can do that, but then the answer should be of the same order.
Okay, I will check after some time.
Okay. So the next one, now we've talked a lot about the hydrogen atom. Now let's talk about X-rays. Okay. So can you just have a look at these sentences, at these statements, and tell me which one is wrong? So our first statement being that the wavelength of characteristic X-rays decreases when the atomic number of the target increases. The second one being the cutoff wavelength of the continuous X-rays depends on the atomic number of the target. Okay, and the third one being the intensity of the characteristic X-rays depends on the electrical power given to the X-ray tube. And the last one, excuse me, somebody wants to join. Yes, Anisha, do you want to say something? Unmute yourself. To mute. Okay, I think she's muted us. Okay, so and the last one being the cutoff wavelength of the continuous X-rays depends on the energy of the electrons in the X-ray tube. So which one do you think is incorrect? Can anybody guess? Tell me. So how will you relate the atomic number of the target from which X-rays are being emitted and the wavelength of these X-rays? So let me give you a hint. I think you've heard about something called Moseley's law, right? If you can use this one, A, B, C, D, or E. I mean, sorry, A, B, C, or D. Anybody? Which is the wrong statement? So what does Moseley's law tell us? It tells us that the
This is
frequency
the
of the,
right.
yes, yes,
Is she,
yes,
she is the wrong about X-rays.
C.
Yes,
Okay,
options.
this is the suggested one. Let us see. Let us try to reason out if that is the correct one or not. If what Amit has said is the right one or not. Okay, so let's start with the first one. And I can clearly see that we have to understand Moseley's law here. And that is, Moseley's law tells us that when we have X-rays, generating from a target, these the characteristics of the X-rays, that is the wavelength. Okay, the wavelength, or rather the frequency, is dependent on the atomic number of the target. How? That is root nu, or the frequency, is equal to A Z minus B. Okay, so it's directly proportional. Okay, the square root of the frequency is directly proportional to the atomic number Z. So that means if we have a material with a higher atomic number, say copper, okay, or tungsten, those will be the X-rays. And you have maybe something, a target like, suppose you have a target like aluminum, okay, whichever has a higher atomic number. Let me just check out which one has the higher atomic number, copper or aluminum. The atomic number of copper is 29 and aluminum 13. So a copper target will give rise to X-rays of higher energy, rather higher frequency. Okay, so let us
What
square
is A
this.
and B?
Yes,
Yeah, what is A and B? They are only a constant or any other thing?
okay. A is, you can say, just constant, okay,
Okay.
and B, what is the use of this B? It could have been just directly just the atomic number, but we have a B here. B is a factor which is coming out due to screening of the electric charge that is faced by the outermost electrons, the valence electrons. Okay, say you have a hydrogen atom, okay, and then you have aluminum. Aluminum has got many shells. I mean, sorry, not many, definitely more than one shell. Okay, two, three shells it has. But hydrogen, the you can say this electron in hydrogen, that will directly see the nuclear charge. But a valence electron in aluminum will not see all of the nuclear charge. The inner shells, the inner electrons will screen that, right? So that is why we have a Z minus B, which is actually the effective nuclear charge, you can say. Okay, so whatever was what Mosley was doing, he was just, you know, seeing what is the energy of the X-rays that are being generated and the targets that are being used, and he plotted them together, and he came up with a relation like this. And of course, to fit them, he had to use some parameters like A is just a constant, nothing else, and B. Okay, so now why is this B term coming? He reasoned out that this effective nuclear charge was what is happening here. What was this is, taking making a big contribution to the energy of the X-rays that are being generated, and that is pretty obvious. So, uh, so if you square this, you will get nu is equal to A square Z minus B square. Okay, so from here you'll get lambda. Lambda is C is lambda nu. Therefore, lambda is equal to C by this nu, that is equal to C a square z minus b whole square. So now can you see that this relation will tell you that the wavelength of the characteristic X-rays decreases when the atomic number of the term of the target increases. Is that all right? This tells you that that point number A is perfectly correct. Okay, next, the cutoff wavelength. Does that depend on the atomic number of the target? How do you determine the cutoff wavelength? I think that is based on, uh, do you know how an X-ray is produced? First of all, let me draw it here.
What is the cutoff wavelength?
Yes, exactly. That is what I will explain to you right now. So, how are X-rays produced? Let me see if okay, I don't have much space. Wait 1 second. Okay. So you see how X-rays are produced? You have a source of electrons. Okay, electrons are coming out from here. You have a high voltage for that. Negative, positive, negative, very high voltage. And you have your target here. A positive voltage here. This positive voltage is falling here. And this entire thing is kept encapsulated and well protected. And there is a window here so that the X-rays can come out. Okay. So when you apply this high voltage, it's around 20 kilovolt, suppose. That means 20,000 volt. Can you imagine? It's huge. So these electrons are emitted from this filament and they get attracted to this target. They want to reach this positive voltage here. Okay. So now in front of this positive voltage, there is a target kept. So that means, and you're applying such a huge amount of voltage. So the energies to which these electrons are accelerated is very, very high. Okay. So 20 keV, just multiply the electronic charge. And this is the energy of the electrons, literally. With such a high energy, these electrons are hitting this target. Whatever you keep here, copper, mostly used. Do you know how X-rays are produced? So when they hit this target, now this target has atoms inside it. Say these are copper atoms. The copper atoms have a nucleus. So when these electrons go near this nuclear field of this copper atoms, or whatever is the target atom, they get decelerated. Okay, so that means they're accelerated, decelerated. So the energies drop when they come close to the nuclear field of these electric fields of the copper atoms, and they sorry, this is wrong. say they just get diverted to some other direction, but with a lower energy. So this is high energy here, and then they get decelerated to a lower energy. So where will this extra energy go? This extra energy comes out as X-rays. That is how X-rays are produced. Okay. Now, if you see the intensity spectrum of the X-rays, you have voltage here. You will not get just a curve like this. You will have some characteristic peaks like this on top of this. These are different. I'll just let you know why. So for now, forget about these characteristic lines. Just maybe it's just a normal curve like this. Okay. Let's consider this is the wavelength. Okay. This is the wavelength. So varying wavelengths of X-rays come out from this, and of course it will be a Gaussian type curve. Now this is called the cutoff wavelength. This lambda minimum. There will always be a certain minimum wavelength whenever you see the wavelength of the X-rays that are coming out from here. There will always be a minimum wavelength. Now why am I saying minimum wavelength? That means X-rays of a certain high energy. You know that the minimum the wavelength, the more is the energy, right? So if this was starting from 0, that means what? Frequency is almost infinite. Energy is almost infinite. That is impossible, because you know that energy is equal to h nu or hc by lambda, right? So you can see that nu is inversely proportional or to this lambda, or energy is inversely proportional to lambda, right? So if this graph was just directly starting from 0, that means nu would have been infinite energy, very very small frequency, extremely infinite symbol. So that cannot happen. That can never happen. There always has to be a limit. Energy can be 0, but it cannot be infinite, right? There has to be a limit in the upper bound of energy of X-rays that are coming out. That means there has to be a limit on the frequency of X-rays that is coming out, or in other terms, there has to be a minimum wavelength. That is called the cutoff wavelength. This cutoff wavelength or minimum wavelength, lambda min. Now you will see that this curve can definitely be 0. I mean very close to 0. That means when the uh, very close to 0, that means very very low energy X-rays. That is possible. But infinite energy, that is impossible. Okay. So this cutoff wavelength, what does this depend on? So I hope this cutoff wavelength is clear. Whoever had asked. Sorry, I didn't see your name at that time. I missed that. Is this okay? What is the cutoff wavelength?
Okay.
Okay. Or the minimum wavelength. Now, what is the energies of these X-rays? Energy of any kind of photon, always know this, will have a universal formula, that is E is equal to h nu. This is just universal. Any kind of photon, any kind of electromagnetic radiation, which does not of course involve terms of a magnetic field, but anyway, photon like entity, and that is equal to hc by lambda. Okay. So this energy E is equal to What determines this energy E? That is the voltage that you have supplied to generate the X-rays in the first place. This 20 kV. If you apply a higher voltage, 50 kV, 50,000 volt you have used, then of course energy, these electrons will have a higher energy. They'll hit the target with a much higher energy, right? And so X-rays of very 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 high energy will come out. So that will reduce your lambda. Okay, that will be the cutoff will reduce. That means higher frequency or higher energy of X-rays will come out. So what was our second point? Let me open that again. This. That the cutoff wavelength of the continuous X-rays depends on the atomic number of the target. From what we have discussed, I didn't see any dependence on the atomic number, did you? It only depends on the voltage which is applied, right? To accelerate the electrons Okay? So this is also so this is the incorrect one. This is 100% incorrect. I don't know about the other two, but this is definitely wrong. It does not depend on the atomic number of the target. And let's say the next one, the intensity of the characteristic X-rays depends on the electrical power given to the X-ray tube. Electrical power means kV that we just talked about. Okay, so I think that definitely depends on it.
Yes,
Okay,
ma'am.
yes, so that E is equal to EV or HC by nu. This V is the accelerating potential. Okay, and that kind of radiation which I have just talked about, that is, this is called Bremsstrahlung. Brem Strahlung. This is a German term. Okay, this radiation is called Bremsstrahlung radiation. Bremsstrahlung in German it means braking radiation. Why braking? Because as if you're braking the speed of the electrons which are which are hitting the target. Okay, whenever these high speed electrons are close to the copper atoms, due to the these atoms have a dense electric charge in it, so that basically has some repulsive effect on the electrons which are coming close to it. So their trajectory is diverted and it is slowed down. That loss of energy comes out as X-rays. So as if you've broken, this is this braking radiation. Okay, now I was talking about some characteristic peaks also, which usually appear something like this. Now, one thing, these Bremsstrahlung radiation or X-rays that I just talked about, you'll be amazed to know this is hardly used. In our experiments, we don't use that. Okay, what we use are the characteristic X-rays. So what are those? These extra peaks, these are the characteristic wavelengths, X-rays. And how are they produced? You see, uh, say this is my nucleus. This is the nucleus of the target atom, the target material, and these are the shells, the electronic shells around it. To it, whatever. And here you have those high-speed electrons coming. Okay. Now mostly they will get diverted, right? Due to this electric field around it, due to the presence of the other electrons. But sometimes they can have, have enough energy. Maybe they did not, uh, you always have those electrons which are lucky enough to not lose much energy and in fact go hit straight inside the atom. They will go straight inside, close to the nucleus, and these electrons which were nicely residing inside, they will kick them out. Those electrons are gone. Okay, they have so much energy and somehow they did not, those lucky electrons which did not suffer scattering from other electrons, atoms. Okay, those lucky electrons will still retain a lot of their energy such that it is enough to move these, to kick these innermost electrons out. So what is happening? So when these are kicked out, there is a gap, right? There is a vacancy. So say the innermost shell had one electron, now had two electrons, now it's just one. So what will happen? The electrons in the shell which is just close to it, okay? Say this is the K line, the first orbit, and say this is the L orbit, the second one. Okay, n is equal to 1, n is equal to 2. So when the electrons in the L orbit will see, okay, there is a space in the orbit which is just in front of it, or the lower lying orbit, it will nicely come down and sit here. It has occupied that space. Okay. So let me remove this electron from here and just make it vacant. Okay. It has come down. Now, since it has made a transition from here to here, it has released some energy. Okay. It is, the nature of the universe and the particles in it to always lower its energy. Like, we don't want so much of pressure. We don't want so much of stress. We want to release stress always, right? We want to unload. Similarly, the electron in the L shell, of course, they have higher energy, okay, compared to the ones which are lying, you know, in the inner shells. So they come down to lower their energy, and in return, they release whatever extra energy they had. These are the characteristic X-rays. And these are the useful ones. Why? Because we know what is the wavelength of these. So in our systems and experiments, of course, we don't want to work with random things. We don't want to work with an extra source which is giving thousands of wavelengths, varying wavelengths. Wavelengths like this, we don't even know what wavelength is coming out, just a range of wavelengths. We don't want to work with that. Okay? these characteristics. Now, why am I saying characteristic X-rays? Why is the term characteristic there? Because this, you see, transition is taking place from the L shell to the K shell. So these are discrete, well established energy levels, okay, of, I don't know which, this energy levels of every element is well established. We know what are the values, we know what are the energies, okay. So from this is said, we can exactly tell the wavelength of the characteristic X-rays. See, like in my, we use copper K alpha X-rays usually, which have a wavelength of around 1.54 angstrom. Okay, now then what is this K alpha? Why did I talk about alpha? That means K alpha, so K means the electrons are coming down, making a transition to the n is equal to 1 to the innermost orbit or shell, and alpha means the ones which are coming just from L, just from the orbit which is lying above it, just the closest orbit, alpha. If I have one electron which is coming down from the next one, that is the M shell, I will call that K beta. Okay. So you will see that usually, wait 1 second. Yeah. Usually in these graphs, let me draw better one, clearer one here. If this say is your X-ray, and this is lambda, this is the intensity, okay. So you will have a peak here, and you have a peak here, say. So this is the K alpha, this is K beta. This is the case always. K beta will always be lesser on the lower wavelength side, and K alpha will always be on the higher wavelength side. Also, the intensity, you can see why is intensity. The intensity of the K alpha line will always be higher than the K beta line. Can anybody tell me why? See the diagram? I know it's messy, but K alpha line is the photon or the X-ray which is released when an electron in the L shell falls to the K shell. And K beta is the X-ray that is released when an electron in the M shell falls to the K shell. So can you tell me why the intensity of the K alpha line is always usually higher compared to the K beta line?
Because we need to apply high voltage to get that first orbit.
Mm, yeah, both are first orbit. For both the cases, the electrons are dropping down to the first orbit only. That is why both of, these are called the K alpha, K beta lines. If they would fall to the second orbit, then they would be called M alpha, M beta, etc. K means whatever transition is taking place, it's falling to the first orbit. Alpha means it's coming from L. Beta means it's coming from higher M. If you have a gamma, then it's coming from even the outer shells. But my question is, why is the intensity of the K alpha line greater compared to the K beta line?
Hmm.
That is because, yes, Amit, you want to say something?
Yes, ma'am. Is this that the frequency from M to K alpha is less than first or
Absolutely, yes, absolutely correct. Yes, because
because
it is
it
obvious. Hmm.
had a
r-
constant frequency?
Right, right. Because that is just the neighboring shell. So the probability of an electron, let me use a different color. So the probability of an electron coming from here compared to an electron coming from here and filling up that gap. There is one space here, one gap, say, because these highly energetic electrons have come and kicked out one electron from the innermost K shell. So there is one vacant space and so many electrons. Obviously, the probability of the electrons which are closest to it, that is the L shell, is highest. They will immediately drop, right? They have a greater probability of transition compared to the electrons which are in the M shell. Okay, so their intensity will always be higher. You will never say that a K beta line is like this and K alpha line is like this. No. Now my question is, why is the wavelength of K alpha line higher than the wavelength of the K beta line? Okay, this is also pretty obvious that you can see the energy difference from, let me zoom it. You can see the energy difference from here to here is lesser compared to the energy difference from here to here, right? This is K beta, this is K alpha. Okay, so higher energy means lower wavelength. Okay, so that's why K beta is lower wavelength, K alpha has higher wavelength. Okay, now let's go back to what we were actually solving. Yeah, so the intensity of the characteristic X-rays. Okay, so we are talking about those particular X-rays which are being generated due to transitions of the electrons from a higher energy state to a lower energy state. So this yes, this depends on the electric power given to the X-ray tube. Okay, so this is not the correct one. Yes, so this is fine because remember this, they might be characteristic wavelength, I mean characteristic X-rays, but ultimately even those are accelerated by the energy, by the accelerating potential, isn't it? And the last one, cutoff wavelength of the continuous X-rays depends on the energy of the electrons in the X-ray tube. That is also correct.
Yes, all correct.
Yes, just the second one was wrong. The cutoff wavelength does not depend on the atomic number of the target. Cutoff wavelength, if this was not there, then this is perfectly okay, right? Because obviously from Moseley's law, there is a dependence of the atomic number and the frequency or wavelength of the X-rays which are generated. But since they have added this term, the cutoff wavelength, that means the maximum energy X-rays that can be given out, that does not depend on the atomic target. Okay, now a numerical based on what we have discussed so far. The wavelength of the K alpha line of the characteristic X-rays emitted by an element is 0.32 angstrom. So what is the wavelength of the K beta line of the same element? So you understand, right? The K alpha line means transition from the n is equal to 2 to n is equal to 1 shell. M to K shell. Sorry, L to K shell. And K beta means M to K shell. Please try to solve this and let me know.
Not getting, ma'am.
Okay. Okay, so here um you know that one by lambda is equal to R, right? Somebody had told this earlier. Is this equation known to you? Where R is the Rydberg's constant. Okay, now, but then why did I put a Z minus 1 instead of Z squared? I think in your hydrogen atom equation there was Z squared, right? But here you have a Z minus 1 squared. That is because we are not talking about hydrogen atom here, first of all. Because can hydrogen atom produce X-rays? Can the hydrogen atom produce X-rays? So this is a very common and basic question.
No, ma'am.
Why?
X-rays are not a visible region, but hydrogen. When we see the hydrogen spectrum, then these lines are in visible region.
Mm, not really. Okay, they can have such, I mean, what you observe, that is correct, definitely. But that is not the answer to why you cannot have X-rays coming out of a hydrogen atom. That is because, first of all, I mean, you won't get the characteristic X-rays because
Hydrogen
now,
have only one electron, so it is
yes,
hard to mm, what is the it is hard to
no,
leave the orbit.
no, okay, fine. You gave so much energy that you gave huge amount of energy. Okay, that is not a problem. You can kick that out electron also, but there is no other electron which will jump down and produce the characteristic X-rays, is there?
Yes, yes.
That electron you kicked out and it has become H plus, and that's the end of story. There is no other electron in hydrogen which will fall down to that vacant space and you have a characteristic X-ray line.
Then helium is cannot produce X-rays.
No, even not helium, even for helium, because there is no other electron in an upper energy level which will fall down and produce X-rays. Okay, just no. So yes, so for hydrogen atom we had just Z square, but since it is not so, I mean it's not hydrogen atom, this is some other target. So we have a Z minus 1 square, which is given by Moseley actually. You see, Moseley had said that root of frequency is equal to A Z minus B, right? This B is the effective, I mean, this is the effective screening. This is due to the screening. Now, for K lines in which the electron is coming down to the first orbit, B is 1. That is what Moseley had said. So we will use, so this is the effective nuclear charge now. So that is why we will use Z minus 1 whole square for K X-rays, alpha, beta, whatever, but the electrons which are falling down to the first orbit basically. So now you put your values, whatever they are. Okay, but uh, you don't need the Z value here. Okay, so use, let us just consider this one because they want the wavelength of K beta of the same element, right? So let us just consider this to be K, okay? So what will this be? So lambda 1 is equal to okay k. Okay, let us first consider the k alpha line. Okay, so here, wait 1 second. Here n1 is 1 and n2 is 2, and for k beta line n1 will be 1 again, but n2 is 3, right?
Ma'am, answer is 2.7 angstrom.
Okay, yes, I also have the same answer. You're correct. So for others, let me just write it down. So 1 by lambda for the alpha will be equal to, okay, and 1 by this will be equal to, say, k. Okay, then you just divide these. So this is equation 1 and this is equation 2. So just 2 divided by 1, and you will get lambda. What did you say was your answer?
2.7
2.7 what unit?
angstrom.
Uh, 2.7. No, it will be here. I have 0.27 angstrom. Just check this out, okay? 0.27. Just check out if you have missed just some decimal places. Okay, you see this will be basically of the same order. This is 0.32. This will be also around 0.27 because 2.7 is too large. Okay, because you see you have k beta. Who wants to join at the last minute? Okay, you see you have k beta, right? So k beta will always have a
0.27.
lower, okay, it will always have a lower wavelength compared to k alpha because k beta is of higher energy. It is falling down from a higher energy state. Okay, so that will have a lower energy always. So 2.7
0.27.
cannot be the right. Okay, so since we have already solved the last problem, so I think you can easily solve this. That characteristic X-rays of frequency this are produced when transitions from the L shell to the K shell. That means immediately you know N1 is equal to 3, sorry 2, and N1 is equal to 1. Okay, this is L, this is K. Shall take place in a certain target material. So you determine the atomic number of the target material and your Rydberg's constant is given here. So once again, just like we've used in the previous problem, 1 by lambda is equal to r z minus 1 whole square, 1 by n1 square, 1 by n2 square. Please put in the values and let me know what is z. And of course you have 1 by lambda here, so that is equal to c is equal to lambda nu, right? So lambda is equal to c by nu, so nu by c. Okay. With just a few minutes remaining, let me tell you this will be 42. Just solve this and see if you get similar answer. This is the answer. This is a similar problem. Let's just skip this. Talk about some new concept. Okay, the Frank Hertz experimental setup. So
What is the answer?
here, pardon, 42. Did you get it?
Okay, okay.
Okay, let's do this one. In a Frank Hertz experimental setup, you have an electron of energy 5.6 passing through mercury vapor, and it emerges with a lower energy. So what is the minimum wavelength of photons emitted by the mercury atoms? Does everybody over here know what happens in the Frank Hertz experiment?
No, man.
Oh, okay. Let me give you a quick recap. I saw that it was done in the previous class, but anyway, here you have a chamber and some filament, electrical filament or whatever, basically that is ejecting electrons. Okay, and what is inside this is mercury vapor, basically inside this gas chamber. Okay, you have mercury atoms, and so you have anode, cathode, setup, whatever. Basically, the current is being measured. So the electrons are reaching on this end. You have negative, positive polarities here. That means an anode and a cathode. And they basically electrons are being ejected at this end and received at this end. They're traversing all this and reaching you. Nothing else. You have an anode and a cathode separated. Electrons are coming out, reaching the other end. You will say that, so what is the specialty of this setup? And they're saying, what is the current passing through this? What is the current received on the other end? Okay, that means the electrons which are received on the other end. Seriously? Why are people joining at 5 p.m.? Okay, so yes, so you might wonder what is there in this setup. Even I was wondering. But the thing is, there is mercury vapor inside it. So, how is that helping? Or what information is putting a gas inside giving us? That is, they saw that when you plot, the current versus voltage, you know, or the intensity of electrons which are received at the other end, and the potential which is given here, the accelerating potential of the electrons, they saw that, of course, as you increase this bias, as you increase this, you will keep on. Seriously, 5 p.m.? Okay. Okay, the ones who are joining now, this class starts at 3 p.m. and okay. So they saw that as you increase the accelerating potential, of course, more and more electrons are reaching, right? So the intensity of the current received at the other end is increasing. Increase voltage, current also increases. More electrons are reaching. But at a certain voltage, there is a drop. Yes, there is a drop. Why is that so? Because there are these mercury atoms here, right? So when you reach, the correct voltage, you have an energy associated with it, right? Electron volt associated with it. So when these electrons have that particular amount of energy, the mercury, the electrons in the mercury atoms, they absorb this and make a transition to the first shell. I mean to the shell just above it. So they understood. So when that particular, okay, let me just show you this in the form of a diagram. Okay, so say this electron is here and this is the next shell. So if you give an energy, so suppose this is an energy 2 electron volt. So to make a transition from this shell, the K shell to the L shell, it needs 2 electron volts, right? But if the energies are lesser than that, say 1 electron volt you're giving, 0.5 electron volt you're giving, the electron is not absorbing that. Even if it's absorbing, it's not being able to, make a transition. So these energies are just passing through, these electrons are just passing through. The energies from that is not affecting these electrons, they're just being randomly scattered, etc. Okay, if it's very low energy, here you see less current. Why? Because they are being scattered here and there. If you increase the voltage, some more electrons, they have a little higher energy, they are being able to reach the other side. And so increase voltage, this increases too. But at the potential, if you give 2 electron volt, this electron will make a transition. So that is the first ionizing potential of mercury, Hg. So all